Okay, last but not least, and I think definitely the best dressed with the jacket. Welcome, Lars. Okay, sorry. Okay, let's not talk about it. Okay, and he's gonna give us the SPM version, and please take it away.
Thank you, Chris. Yeah, I realize I'm the only one standing between you and lunch, so I'm trying to make this really practical. And I will give you the SPM perspective on fMRI preprocessing. So SPM, a lot of you know, is an abbreviation for statistical parametric mapping, and it's a software developed in London for a quarter of a century now, which deals with functional imaging analysis in many more cases than just fMRI. You can analyze MEG, EEG, PET data with it. But what I like best about SPM is its philosophy of being a free software that is MATLAB based, so it's an accessible code. You can look under the hood of every program just within MATLAB, so platform independent, and you can debug your software and interactively operate on it and access and contribute with your own code. So that's why I really like MATLAB, and we'll see some examples today that you can all download and try out for yourself. So there will be a lot of slides today. I will not go into detail. They are downloadable along with the code, and you should really go out for yourself and check these examples to learn about how to use SPM. I will first talk about the general preprocessing pipeline of SPM and a very fundamental concept within that, which is the batch editor, and then talk about what Mark also mentioned, how to monitor actually and compare preprocessing pipelines within SPM. Then we will go to multi-subject pipelines, because that's why we do all this pipelining in the first place. And I will finish with integrating your own code and more sophisticated toolboxes within the SPM preprocessing pipeline with the example of physiological noise modeling that we use in our lab. So let's get started. This is the overview of SPM for fMRI. It not only contains the preprocessing steps, which are here, spatial preprocessing, but it also contains the whole estimation of the linear model and the statistical inference process. And some of the preprocessing steps we've heard about today are actually hidden in the model, as we already seen in FSL. So temporal filtering is part of the modeling, and also physiological noise correction goes into the modeling. If you start SPM, fMRI in MATLAB, you will see this GUI, and the structure actually resembles this distinction between the preprocessing, which is in the top part, and has all these components like realignment, slice timing correction, co-registration, up to smoothing. And there's also the noise modeling part in the specification of the first level analysis. Most importantly, this button here is calls the batch editor, and actually the way SPM is working right now, each of the buttons on top, you can click here, all of them will lead you straight to the batch editor. So it is really the central component in operating SPM via the GUI. So as you've seen with the buttons, there are quite some different names for different image registration steps in SPM, and they usually depend on what input images and what allowed transformations these image registrations have. So realignment refers to the intramodal image registration to align functional images of the same geometry and contrast. And it allows for rigid body transformations, translations, rotations. It's also based on the normalized correlation. I think it's a very similar algorithm to what FSL uses. The co-registration step is also very similar. It's the intermodal registration between the functional and the structural image. You've heard that the T1 image has a very different contrast from the T2, but you still have to co-register them. And since the geometry of these sequences can be different, we allow for affine transformations, both rigid body, but also stretching and shearing of your imaging volume. And when we talk about normalization in SPM, we usually mean a multimodal registration nowadays. So images of different contrast can be warped together, T1, T2 images, to a template space, the MNI standard space. And here, because we have many more options there, how the images can be distorted, we will also have a lot more applicable transformations that are represented with voxel-wise deformations, which are called deformation fields. So if you put this pipeline together, you start with a fMRI time series that comes out of the scanner. You perform the realignment and get a nicely motion-corrected imaging time series together with a mean functional image. You will take the structural MRI and co-register one to the other and write out imaging headers which represent these affine transformations. So again, we don't want to really interpolate each single step of the way, so we actually don't touch the imaging matrix, we only change the header of the nifty files. And in the next step, we do some segmentation of the images, of the structural images, with the help of tissue probability maps, which is actually already part of the normalization in SPM, because we get some deformation fields from that, from the procedure of segmenting a structural image given tissue probability maps in our standard space, and we can use these deformation fields to write out our functional images in the MNI space. Finally, we do some smoothing, and we end up with data that is ready for the linear model. So this is the overview of the pipeline, and yeah, you've seen that the realignment is in there, the co-registration, and there's also this combined approach of unified segmentation for normalization. And I want to give you just two theoretical bits of the SPM processing pipeline, just to give you an idea what the outputs you see later on mean. So for the co-registration, I want to explain what the joint histogram is, and that refers to the fact that you are co-registering images of different contrast. So let's say you have a CSF voxel in the EPI. It has a very high intensity that shows up in the histogram at a very high signal intensity peak, whereas in the anatomical image it's very dark and still refers to a peak in the histogram. If you put a joint histogram, which actually takes for every voxel, it looks at its intensity in the T1 and in the T2 weighted image, you come up with a plot which looks like that, and our voxel will actually be put at this position because it has a very high intensity in the T2 weighted and a very low intensity in the T1 weighted image. Now this is an approximation of the mutual information that one image carries about the other. So even though the contrast is different, every CSF voxel will be bright in the T2 contrast, but it will be dark in the T1 contrast. So this joint histogram tells you something about how well these images are aligned in terms of when the peaks are sharp in this joint histogram, you will put all voxels of the same tissue types in the same bin. So the sharpness in this joint histogram really matters, and that's what you should take from this slide. And for the unified segmentation, you might wonder, why do we do it in such a complicated way with all these tissue probability maps if we only want to get this image into standard space? And the reason for that is that normalization is much more difficult because brains are so different. So there's no simple similarity measure. There's a lot of possible transformations because of the gyrifications of the brain. And there are different imaging sequences with which you acquire your data. The contrast, the geometry, everything can change. There's, of course, artifacts and noise that differs between subjects. And there's also coil properties and homogeneities that change the intensities in your image. So what the idea of unified segmentation is that normalization would be much easier if we knew something about the tissue type of each individual voxel. So if you had a segmented image, we could normalize these individual tissues. On the other hand, if we knew where the voxel was roughly in the brain, like its anatomical region, so if we had a normalized image, segmentation would be much easier. So that motivates this unified model of segmenting and normalizing at the same time. And it's been around for 10 years now. It's called unified segmentation. And it's a Bayesian generative model of voxel intensities that basically generates voxel intensities from tissue class probabilities, these deformation fields that alter the tissue probability maps, and these bias fields of the coil. So just to give you an idea, the probability of a certain voxel having a high intensity is much higher if it is in the white matter for a T1 weighted image. But if it's in the CSF, it's much more likely that this voxel will have a low intensity. So the way SPM models that is with a Gaussian mixture model. And it has priors on what individual voxels can have as tissue type, which are in MNI space. And then what SPM tries to do is to estimate deformation fields that can map your tissue probability maps to the actual distribution you see in the individual subject, and combine that with the bias fields for the more smooth changes in the intensity. Yeah, and this is important because we will later on talk about these deformation fields or see these deformation fields when the processing is performed. So now you should have the theoretical background to understand that whole pipeline. But now the question is, how do we actually get from this pipeline to a batch that can be used in SPM? And really the elements of a pipeline in every preprocessing pipeline are threefold. There are modules which take certain input images and create output images. Then there are dependencies that explain how the output of one module can be the input to another module. And then there is the data which is subject specific. And if you call the batch editor, you will see an exact resemblance of these three ideas. So you will see on the left side certain modules like realignment, segmentation, smoothing. You will see dependencies that tell you how an input becomes an output, or an output becomes an input to another estimation step. And you also see the subject-specific input data. So the batch editor has been around for, I think, more than 10 years now. It's been really integrated since SPM 8, and it's much better now in SPM 12 as well. You can call it via the GUI, clicking the batch button, or you can just call SPM Jobman in MATLAB, and then this GUI opens. And we will actually now go through a demo that you can also download for yourself, which takes a simple preprocessing batch that comes with SPM in this batches subfolder, and some data from our lab, which I mainly took because it's more recent, more modern data than what we have on the SPM website, and it has physiological recordings, which we need later on today. So everything you see here, we will now go through, so we don't have to read that now. Yeah, so if we go into MATLAB, you download the code, and you run this piece of code, init reset example. It will create some subject folders and subfolders in this, which actually contain the fMRI data, the log files, and the structural data. And you also see these batches, and we start with the one in the demo 1 folder by just calling SPM. Actually, this video is sped up already. It takes about 10 minutes to run this whole batch. And once we've loaded this batch file, you will see these modules and dependencies and can see what happens in the different GUI parts. So you see there's the co-register part with the reference image, which is the segmented image. And then in the segmentation, you see as an input image actually the subject-specific volumes. So there are these three components. On the left, you see the modules. You press play, the realignment starts, and if you go to the subject folder, to the fMRI subfolder, you will see already that there are new files created, for example, the realignment parameters, and SPM outputs the translation and the rotation parameters for this subject. Meanwhile, we're performing another step, the unwarping procedure, which deals with these API deformations and their interaction with the movement. If you had a field map, which we don't have, you could also correct for static deformations. And in the background, there was already the co-registration running, and here you see these joint histograms that show actually not so much improvement here, but there is kind of a sharpening in certain areas, maybe. And in the background, the SPM already performed the segmentation, and here maybe you see it. It also wrote out the normalized images and smoothed them. So a lot has happened, and you haven't seen a lot. So everything you can get from SPM at the moment is a PostScript file that saves all these realignment outputs in the graphics window and the co-registration outputs. And here I actually have an example of co-registration where where you can really see that the joint histogram got a lot sharper through the co-registration. Now this brings us to the monitoring aspects for the pipeline. So how do we, now that we automatize everything, we don't see a lot. So when something goes wrong, how do we notice that something went wrong, and where did it go wrong? And the answer again is the batch editor. So we not only automatize our pre-processing pipeline, we also automatize the way we monitor our data. What is needed for that are suitable performance measures. I mean, for a single image, it's really easy to say, well, a structural image is good if it shows a lot of detail, if there's no noise in the image, good contrast, the geometry has a high fidelity. For time series, it's not so easy to say what is a good time series. And there, what I propose here is to use different statistical images to assess the quality. What I mean by that is to look at the mean of a time series, which is depicted here. There you can see artifacts that are consistent over all volumes you acquire. To look at the standard deviations to see typical localizations of fluctuations. To look at the temporal SNR, which is just the ratio of the mean and the standard deviation image, which gives you an indication of the sensitivity you have, because F contrast, T contrast all deal with this ratio of contrast to noise. The signal to noise is a good proxy if you have no model for that. So you see, for example, here the coils see less in the center of the brain than in the cortex, so you would have less sensitivity there, but that's normal. And there are also these extremal statistics, like difference images. For example, what we see here is the difference between the odd and the even images, which removes drift and should resemble a thermal noise image in a way. And we see this maximum absolute difference image, which actually tells you between two consecutive images, what was the largest deviation you've seen. And if there is strong movement in one dynamic, in one volume, you would see that it looks very different than this maximum image here. This brings us to the second demo, which does a complete pre-processing and monitoring pipeline for a single subject. It's actually, again, based on a batch that comes with SPM, but it has been augmented by a batch within a batch, which I wrote, which is called Batch Report Quality, that actually visualizes and saves these quality measures I just introduced after each of the pre-processing steps. Yeah, here's the explanation again, how you can do it. The important part is this last part here, this batch job, which is run, the quality report, which creates for each pre-processing step these statistical images and displays them. So let's have a look again. We clean up a bit. We just call this init reset example script again, which removes now all processed data. We start fresh, and then we just call the job manager directly from the command line with the name. It's in the demo 2 folder, and with the interactive option to actually so that we can actually display it. So you see, it's a bit more sophisticated. We create a brain extraction in this batch, and then you see these different reports created and subfolders created for all these statistical images. So let's run it. Yeah, let's now again sped up. Would probably take another 10 minutes to run this. The same things happen as before. That's really not very interesting. But in the very end, you see actually that there are these output images created. And that's using a tool we will look at in a moment. We can zoom in a bit. You see the mean image here. You see the SNR image here. You can even display the file names to see what image you actually display here. And meanwhile, we see the same output after the co-registration. Looks a bit different. And we can actually also look at it after the normalization. So you see now it's warped. And we can overlay the edges of the structural image onto all the others to see how well the co-registration worked. And finally, we can play around with these lines a lot and with these display options. So everything finished, in the end there is a PostScript file created which is called report quality, which basically summarizes all these graphical outputs, so you don't have to stay at your computer, you can just look at the PostScript file afterwards. The output of this script is basically, here you see this subfolder report quality with all these statistical images, and you can not only use the PostScript file to look at them, but you can actually call them within MATLAB. And yeah, I would also emphasize that it's a good idea to look at all these statistical images. And the powerful tool for that is this check-reg, this SPM check registration tool, which you can call from the batch editor or from the command line. And it's actually some new features now in SPM 12, so you can also do this movie plot in SPM 12. And what I already showed in the demo is it has a lot of neat features, but they are somehow hidden. So just right-click once you've called this check-reg tool, and then you see things like you can anatomically label your voxel, you can add certain activity blobs, you can do the edge detection, the header info, contrast changes, and so on. And just here is an example you can try at home. If you have done the pre-processing pipeline, for example, you can look at the SNR image after each processing step. So that's what I've done here with this code. And this is what it looks like. So you see, for a single voxel, I displayed the intensity of the SNR. In the raw, it's about 27. After realignment, the SNR massively increases to 47. The co-registration and normalization, because they don't change the statistics, they just move around all images the same way. Don't change the intensity a lot, but then if you do the spatial smoothing, you get a massive boost in temporal SNR. So this is actually a very good pipeline. Now, what is a bad pipeline now? There's also a demo for running artifact subjects with the same code. You can try, and I just report to some of the quality figures now here from 3 subjects. This is the first one. Well, the structural image looks good. The mean image also looks kind of good. There's something weird about the standard deviation, and definitely with these difference images. What actually happened here is that the subject had rotated by a lot in one of the volumes. So that's how you spot this. Then you can look at the second subject, and you see that everything kind of looks distorted in the finally smoothed images. It's not really clear from this step what went wrong. But if you go back to the very beginning, you actually see that you had a flipped structural image, and the tissue probabilities maps were kind of mirrored to that. So you couldn't really segment this image properly, and all the normalization failed. A bit trickier even is this one, where the segmentation works perfectly, but you see that the smooth functional images actually are somewhere else. They're not in standard space. And if you look at the first the raw data, you already see something went wrong here. The whole functional image time series is shifted by 10 centimeters, and that's actually too big to be co-registered. So, and the subtlety here is, if you just looked at the functional time series itself with a check-reg, you wouldn't see it, because the center of the imaging matrix is always displayed in the center, and 0, 0, 0, the center of the MNI space, could be completely at an off position. So finally, doing multi-subject pipelines is very easy once you've set up such a single subject pipeline. And the only thing you have to take care of is data organization. So you create one subfolder one study folder where you put all your code in and your template batches. And then the modules and dependencies of your pipeline will stay the same between subjects. So the only thing you have to take care for is the third part of these pipelines, which is the subject-specific data. And what you have to do is, what I recommend to do is creating the same subfolder structure for all your subjects. So always put here we have 2 subjects, always put the fMRI data in the fMRI subfolder, always name it fMRI.nifty. Same for the log files and the structural data. And with this, specifying the subject-specific data reduces to just specifying a new folder. And what you have to do then is looping over the subjects. So once you've tested and optimized the batch for one subject, you clear the subject-specific values from this batch just by right-clicking and say clear value. And then there's an option to save this batch along with the script in SPM, which creates this job file that we've seen before, but it also creates an M file, a MATLAB script file, which is basically just a loop over all subjects, and it has some template inputs that you have to fill out yourself. And these are, in this case, the subject folder and the structural and the functional data. So here I've just done that. So you see I filled out my subject path and my functional and structural image, and I combined them just with simple MATLAB commands. And then finally, I again run the SPM job manager, but this time with another option, run, which doesn't do the interactive stuff, but just runs the batch directly. And well, what you still have to do is you have to look at your data. And I think this check-reg tool is, again, a very good idea to use here. And you use it the same way as for the single subject data, but this time, for example, you could look at the final SNR image for all of your subjects after smoothing. There's a demo for that as well. We won't go through it now, but you can just have a look at that. And the demo also explains comparing different pipelines, for example, if you do slice timing first or last. And the last part of the talk, I want to talk about integrating your own code and toolboxes into the pipeline. And the first question is, of course, how do you do that? Can you do that in the batch editor? And it's actually very simple. There's a basic I/O module that can run any MATLAB function, and you just have to specify how many input and how many output parameters your own function has. And that is very neat, because then you can also make use of all these dependencies. So one simple example where this would be useful is if you had your realignment parameters calculated by the realignment module, and you wanted to create these 24 regressors of the derivative and the squared motion parameters. So you can just call your own function to do this after the realignment parameters have been estimated. And I think this is also the only case where it makes sense to use this facility. So if you have output data from your pipeline that you want to input at a specific point in your pipeline into your own code. Otherwise, it's much more efficient to use MATLAB itself. And more complex than just running a function, you can also write your own toolboxes for SPM and integrate them with a batch interface. And we have done that for physiological noise correction, actually implementing a lot what Rasmus has shown you before, mostly these model-based approaches, retro-ICOR, and these cardiac and respiratory response functions. And the toolbox actually takes physiological monitoring data from ECG, PPU, breathing belt, preprocesses them in terms of peak detection, denoising, because especially at high field, ECG data is really noisy, and then models the time series of physiological regressors that can then be input as nuisance regressors into SPM. So this is, again, the noise reduction itself, part of the general linear model. And if you install this toolbox and put it into a specific folder, the toolbox folder of SPM, you will actually see it in the batch editor as a new item. And and it has a lot of parameters, since we want to make it really versatile, so it can read GE, Siemens, Philips log files directly, synchronize them with the scan timing, and then preprocess them in terms of peak detection. And finally does the noise modeling with retro-ICOR, or these the heart rate and respiratory volume variabilities. And once you've estimated these regressors and put them in your model, of course you have to assess their performance, and that's actually done in the results report, which actually can take an arbitrary contrast and report in the graphics window how much variance is explained by such a regressor. And there's a tool in our toolbox where you can not only look at the glass brain, but also show the structural underlay with a contrast automatically. And then you end up with localization of physiological noise that hopefully resembles what is there in the literature. The last demo I will show just does that. It performs the whole single subject analysis except what we've seen before. So once you have your smooth images, it creates your conditions of interest, creates your multiple regressors that include realignment and physiological noise regressors, and then estimates certain contrasts for quality assessment. Let's have a look. We go to this batch folder and we call again the job manager. interactively, just to have a look. Yeah, we input the onsets file from the behavior, the physiological log file, and also the realignment parameters. Then we estimate our conditions of interest, but we also estimate our regressors, our nuisance regressors, and then they can be input as dependencies into our model specification. And finally, we can estimate the model, report the contrast. We are quite liberal here because we only have 100 scans. And in the end, we report all these contrasts with this custom function of ours. And output all the graphics output into this physio.ps file. So let's run it. Yeah, so the toolbox is running. It reads your physiological log files, creates retroarchal regressors, and then the design matrix. Now the model estimation is already performed. You see a lot of these physiological noise and realignment regressors, and then all the outputs are reported in the glass spray with all the peaks. And each of those is output actually into this SPM PostScript file. Each of these plots you've just seen. Plus there are now these plots which have the structural underlay, which are output into this physio.ps file here. And you can look at them offline. Yeah, so I really recommend to try out all these demos at home. And if you have any questions, just write me an email. In conclusion, I want to say that setting up a pre-processing pipeline in SPM, you should use the batch editor because it's just the best way for reproducible and documented pre-processing. You can save it for each individual subject automatically, and you always know what you've done. To monitor and compare pipelines, you can use the batch editor, primarily the check registration tool and the automatic creation of statistical images that you assess after your pre-processing. And for multi-subject pipelines, you don't have to do a lot more. Just create a template batch and the same subfolder structure for all your subjects, and yeah, basically a loop in MATLAB over these subjects. And integrating your own code is very versatile. You can do it anywhere in the pipeline within the batch editor, and you can even go to length to complex toolboxes like the one for physiological noise correction. So with that, I would like to thank you for your attention and all these people for input to this talk.
Any really quick questions?
I have a simple question. When combining FSL with SPM toolbox during the data analysis, is there any problem in the data transferring or anything need to be noticed?
So you mean when you mix different modules from SPM and FSL? Or?
Yes. Yes.
Well, I actually I'm not aware of problems there. I think there's one subtlety, for example, in certain ways of how you deal with the headers. So, for example, I think if you use FSL view, it shows you the matrix of the image, and if just the header of your image is changed, I think there's no reinterpolation. Whereas if you look at it in SPM, you see the interpolated values, and SPM creates this fMRI.mat file for the realignment that is not really nifty standard. So there are some subtleties with the headers. That's the most I'm aware of. And other than that, you just, I think, have to make sure to have the data available at the right time point. So I think use the best tool for each step.
Okay.
I have a very quick question, just for both the SPM and FSL. I was wondering, the first level analysis is performed before or after you align our image to the standard template?
Yeah, it's performed after you do the normalization to standard space. Yeah, that's the default in SPM. Yeah.
Is it better to perform this at the native space of the subject?
Assuming so.
Is it better to, before you change the image and perform the first level analysis?
I guess it depends on the quality of your normalization procedure. So if you have a good normalization procedure, it shouldn't make a big difference. Of course, if you're interested in anatomical detail that differs between subjects, and you get rid of some of these differences, like gyrification, then you might lose power.
Because the question is because the resolution of a functional MRI is not very good, and then probably some orientation, maybe you need to rotate the image or something like. Then also partial volume. After you interpolate the data, have partial volume issues. I just want to get your opinion. Which one could be, should be better?
I think it's an empirical question. You could try both with it.
I think it's an empirical question. I don't think there's an across-the-board answer, probably. But anyways, okay, so thanks, everybody, for holding out so long, and thanks to speakers. And Mike, Ray just mentioned, please give feedback and tell us how we can make this more useful for you, and thank you. That was great. This year was very good. Very enjoyed. Actually, so it's really SPM 12. You got the movie.
Yeah. Actually, I only realized when I made it, because if you call it, I don't even know whether it works within the GUI or just if you call to check registration from the job manager. Because if you use the GUI, you always see these frames, and if you select